let's say that I have two non-zero vectors. Let's say the first vector is x, the second vector is y. They're both a part of, or a set, they're both in the set Rn, and they're non-zero. Non-zero. It turns out that the absolute value of their, let me do it in a different color. The absolute, let me do it in a, this color is nice. The absolute value of their dot product of the two vectors, the absolute value, remember this is just a scalar quantity, is less than or equal to the product of their lengths. And we've defined the dot product, and we've defined lengths already. It's less than or equal to the product of their lengths. And just to push it even further, the only time that this is equal, so the dot product of the two vectors is only going to be equal to the length. So this, the equal and the less than or equal apply only in the situation, let me write that down, only in the situation where one of these vectors is a scalar multiple of the other, or they're collinear. They're just, one's just kind of a longer, shorter version of the other one. So only in the situation where, let's just say, x is equal to some scalar multiple of y. And these inequalities, or I guess this equality and this inequality, this is called the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. So let's prove it, because you can't take something like this just at face value. You shouldn't just accept that. So let me just construct a somewhat artificial function. Let me construct some function of that's a function of some variable, some scalar t. Let me define p of t to be equal to the length of the vector t times the vector, some scalar t times the vector y minus the vector x. And it's the length of this vector. This is going to be a vector now. Is that squared? Now, before I move forward, I want to make one little point here. If I take the length of any vector, of any real vector, so the length of any real vector, I'll do it here. Let's say I take the length of some vector v. I want you to accept that this is going to be a positive number, or it's at least greater than or equal to 0, because this is just going to be each of its terms squared, v2 squared all the way to vn squared. All of these are real numbers. When you square a real number, you get something greater than or equal to 0. And then you sum them up, you're going to have something greater than or equal to 0. And you take the square root of it, the principal square root, the positive square root, you're going to have something greater than or equal to 0. So the length of any real vector is going to be greater than or equal to 0. So this is the length of a real vector. So this is going to be greater than or equal to 0. Now, in the previous video, I think it was 2 videos ago, I also showed that the magnitude, or the length of a vector squared, can also be rewritten as the dot product of that vector with itself. So let's rewrite this vector that way. So this is equal to, the length of this vector squared is equal to the dot product of that vector with itself. So it's ty minus x dot ty minus x. In the last video, I showed you that you can treat multiplication, or you can treat the dot product very similar to regular multiplication when it comes to the associative, distributive, and commutative properties. So when you multiply these, you can kind of use these multiplying these two binomials. You can do it the same way as you would just multiply two regular algebraic binomials. You're essentially just using the distributive property. So but remember, this isn't just regular multiplication. This is the dot product we're doing. This is vector multiplication, or one version of vector multiplication. So if we distribute it out, this will become ty dot ty. So let me write that out. That'll be ty dot ty. And then we'll get a minus, let me do it this way. Then we get the minus x times this ty. So you get, or instead of saying times, I should be very careful to say dot. So minus x dot ty. And then you end up, and then you have this ty times this minus x. So then you have minus ty dot x. And then finally, you have the x's dot with each other. And you can view them as minus 1x dot minus 1x. So you could say plus minus 1x, right? I could just say view this as plus minus 1 or plus minus 1. So this is minus 1x dot minus 1x. So let's see. So this is what my whole expression simplified to, or expanded to. I can't really call this a simplification. But we can use the fact that this is commutative and associative to rewrite this expression right here. This is equal to y dot y times t squared, right? T is just a scalar, minus, and actually this is 2. These two things are equivalent, right? If they're just rearrangements of the same thing. And we saw that the dot product is associative. So this is just equal to 2 times x dot y times t. And I should do that in maybe a different color. So these two terms result in that term right there. And then you have if you just rearrange these, you have a minus 1 times a minus 1. They cancel out. So those would become plus. And you're just left with plus x dot x. And I should do that in a different color as well.